Good morning, everyone. Can you hear me?
Good morning.
Okay.
Good morning.
Good morning, everyone. So, welcome to the first webinar of TWIN-RELECT project on bridging EU innovation on reliable electronics design. I'm Mikis Tsoumanis. I'll be coordinating this webinar today. Before we begin, please note that this webinar is being recorded for documentation, dissemination, and reporting purposes. So by attending this webinar, you give your consent to the recording. So let's start to see a quick look to the program for today. So we have 6 speakers presenting their EU projects that advance research and innovation in reliable electronics, as well as their objectives, recent achievements, and future directions. Of course, the goal is not only to disseminate the research outcomes, but also to foster collaboration in this field. So we encourage all participants to engage with the talks by sharing their thoughts, their questions, add comments in the chat throughout the webinar, the session. So let's start with the first presentation. Unfortunately, Mr. Soteriou could not be with us due to some personal issues. So Nikos Hadjivangelis will present TWIN-RELECT project. So Nikos, can you share your screen? Just a second.
Yeah, just a second.
Yeah.
So can you see my screen?
Yeah.
Okay. So good morning, everyone. Welcome to the first TWIN-RELECT webinar on bridging EU innovation in reliable electronics design. I'm Nikos Hadjivangelis, PhD student at the University of Thessaly, and today I'm going to present you the TWIN-RELECT project. Unfortunately, Professor Soteriou could not be with us today due to some personal issues, so I hope I will be enough to replace him. So TWIN-RELECT stands for Twinning for Excellence in Reliable Electronics, and why we need reliable electronics. Most of you probably already know the answer, but for those not so familiar with the topic, reliable electronics are important for mission-critical systems that cannot withstand any failures, and a simple failure may result in catastrophic events. Such systems are space applications, avionics, automotive, nuclear power plants, etc. So our goal in the project is to establish a novel cross-layer methodology for designing reliable electronics, and with a strategic collaboration with the advanced partners of the project, we plan to elevate the capacity of the University of Thessaly in this field. The project started last year in October 2024, and it will end in September 2027. It is coordinated, of course, by University of Thessaly, and specifically by the Circuits and Systems Lab located in Volos, Greece. And the project partners include the IHP Microelectronics located in Frankfurt Oder, Germany, the University of Montpellier and CNRS located in France, and the University of Manchester located in the UK. So these 5 partners form a team of 23 researchers, each with their own expertise. The Circuits and Systems Lab from University of Thessaly has a strong knowledge on ETA and CAD tools. IHP has a strong knowledge on system architectures and fault-tolerant designs. The University of Montpellier, and specifically the RADNEXT group, has years of experience in radiation testing. And finally, the Advanced Processor Technologies Group from University of Manchester is an expert on neuromorphic computing technologies. So let's talk about the pillars of the project, starting with the research management and administration. Here, the goal is to elevate the University of Thessaly capacity at managing EU projects, and the key objectives here include the establishment of an international projects office to support the preparation of project proposals, as well as provide guidance for the coordination of these projects. A research management handbook will be developed also as a best practices guide for managing EU projects. We will also implement agile management tools. And finally, training will be provided both to research and administration staff through the organization of research management and administration workshops. With these means, we hope that our university will become more efficient in managing EU projects, and also it will become more effective in such calls. The second pillar of the project is the strengthening of University of Thessaly research profile and international collaborations through strategic networking and visibility. This will be done by a series of key actions. And first, we will host high-impact events such as scientific workshops, business forums, special sessions at major conferences and the final international symposium in Greece, with the main target being, of course, to build a network of stakeholders from both the academia and the industry. Also, through the open access publications, the social media, and other outreach means, we plan on elevating the visibility of our university. And finally, we want to increase the educational attractiveness of the institution by upgrading courses and promoting international co-supervision of master's and PhD studies. With these actions, our goal is to make the University of Thessaly a recognized hub in the EU in the field of reliable electronics. Some of the key activities of the project include the publication of 12 conference papers and 10 journals, the organization of 4 training schools, 1 at each partner institution, 3 scientific workshops organized in Volos, Greece, 5 research management and administration workshops, 2 business forums also organized in Volos, Greece, 3 webinars, 2 special conference sessions, and a final symposium in Greece. Also, the PhD students from University of Thessaly will spend up to 10 months at the partner institutions for training, and also the partners will conduct short-term visits to the University of Thessaly to provide lectures and conduct research here. Also, we plan to visit some research centers such as CERN, CNRS, ESA, and attend, of course, conferences, workshops, and other outreach events. And finally, some irradiation experiments are planned during the project, such as ionizing particle irradiation, gamma X-ray irradiation, laser, accelerated aging, and EMI. So, as you can see here, we had many events during the first year of the project, starting from October 2024 with a kickoff meeting, and then in January, the first training school at University of Montpellier. We also attended the tight seat window school at IHP in February, and in May, we also visited again IHP for the first research management and administration workshop and the second training school. In July, we hosted in Volos the first scientific workshop and the second research management and administration workshop. And in September, we attended and presented the project in the Twinning Info Day organized by our colleagues from AIDA for EDGE project. And we also hosted our first business forum. And today we are having our first webinar. So in the future, we also have many more events to organize. This is a rough schedule of the events. So stay tuned, and of course, you are all invited to join us. So the third pillar of the project is, of course, the research, and the most interesting for us. So as I said earlier, we are planning on developing an EDA tool flow for reliability analysis. And here our vision is to bridge the gap between device level analysis and system level analysis by integrating fault modeling throughout this entire design stack, from device level to transistor level to gate level to system level, while also incorporating fault mitigation techniques, allowing the designers to improve the resilience of their systems. So I will talk a bit more about this EDA tool flow. As you can see here, it is comprised from 5 tools in total, starting from the device level, where here we have the Predixi tool and the eCourse tool, which both of them were developed by University of Montpellier and CNRS. The Predixi tool offers a Monte Carlo-based SCU and SCT cross-section estimation, and eCourse is a TCAD simulator. In the transistor level, we are planning to use SPICE simulations using the help of our EHP. And here we will characterize standard cells and application-specific cells in order to provide to export gate level lookup tables, and then feed them into the gate level, in which upset, the tool developed by our university, will be used, which performs STA-based fault analysis, and then use the analysis data into the system level using the tool Ember, which is a cycle-based fault injection framework, which outputs the fault masking probability, which then can be used again by upset in order to guide the STA-based optimizations to export new, more resilient design.
Ωραία, αυτό θα χτίσουμε πίσω.
Sorry?
Μάλλον να μιλήσουμε. Εντάξει, μείωσε το. Μπράβο, ευχαριστώ πολύ. Έλεγε γεια.
Okay. So I will move on to talk about some first results of our research throughout this year, starting from describing the upset SCT analysis framework, which is a probabilistic STA-based SCT analysis framework, supporting SCT generation through the double exponential current source model, SCT propagation using static timing analysis principles, and supporting timing models such as NLDM, CCS, wire models such as lambda-RC, pi model, detailed RC, and of course supporting 2 propagation modes, the vanilla mode, which is a worst case analysis, and the detailed timestamp based mode, which offers higher accuracy. As you can see here in the photos, the vanilla mode produces a higher pulse compared to the detailed mode here, in which here at every timestamp, Boolean evaluation is performed in order to obtain the pulse at the output. Also, the probabilistic analysis is used in order to model the state of the design at any given time, so that we don't need to load vectors and analyze the design through the vectors. So every pin in the circuit is associated with a probability of being at logic 1 or logic 0. And through these probabilities are then be used in order to estimate the probability of the fault being propagated at the output of the gate, and then eventually reaching the flip-flop input or the primary outputs of the design, the STA endpoints. Also, offsets supports a design hardening methodology through a closed-loop SCT optimization methodology. And here we perform gate-level SCT mitigation techniques, and the goal is to offer fast SCT optimization with minimum power performance at area overheads. Here, some of the techniques that we are currently investigating is the pin assignment, the gate resizing, the insertion of cascading inverters, of course, TMR and SCT filter insertion. We are also investigating SCT-driven placement, fan-out decomposition, and the insertion of charge sharing logic. And here in these tables, you can see some first results. In the graph here, you can see the accumulated pulse widths at the endpoints. This is the accumulation of the pulse width of the SCT pulse widths arriving at the endpoints of the design. And here you can see the TNS before and after the optimizations. So on average, we see 53% improvement on the pulse widths and 40% worsening on TNS. Of course, these results are subject to change and get better during the course of the project. This is a work in progress, as I said. Another work that we did is to combine two simulation tools in order to provide a more accurate SCT analysis flow. First, we used the PredictC tool from University of Montpellier in order to have realistic SCT generation modeling, and then Upset for fast SCT propagation and software rate estimation, allowing us to analyze large-scale designs. The flow we used can be seen here on the right. We modeled the technology standard cells in PredictC, and we performed SCT simulations in order to obtain realistic voltage pulses caused by particle strikes, and then import them into the Upset tool to perform SCT propagation and evaluate the probability of error at the design's flip-flops. This work was used to target clock networks, and this work was presented actually last week in Barcelona in the DFTS 2025 conference. And the results here of this work showed that an SCT at the clock network may have significant probability of causing errors at the flip-flops, even sometimes 80%, 88% probability of causing error, which is very high, considering that a single clock buffer may drive a large number of flip-flops. Another work that we did was the reliability analysis of dynamic neural networks. And here we used fault injection method. We performed fault injection in NVDLA MAC arrays for stacked faults at critical gates. And our case study was on slimmable AlexNet, as can be seen, with 4 increments. You can see it here in the picture, and using the CFAR10 dataset. The results can be seen by these graphs here. K is the number of MAC units, and as you can see, higher number of MAC units mean more resilience here. So a conclusion of this work can be that adding more MAC units can can work as a, let's say, a methodology of hardening your design, because a MAG unit will eventually perform less operations. So as a fault, a single fault can in a MAG unit cannot affect many operations. Another work that we did recently is the investigation of ML-based SET generation. Here we perform SPICE simulations and the IHP 130 nanometer PDK, and there's a test circuit, you can see it here. And then we use machine learning models to predict the generated SET pulse using parameters based on output capacitance, particle charge, cell drive strength, and PVT corner. We developed ICT lookup tables, of course, through using the SPICE simulations, following Liberty standards in order to perform interpolations and also predict the pulses with this way. And our experiment comparisons include SPICE against machine learning and SPICE against lookup table interpolations. So as you can see here in the picture, this is the blue line is the actual pulse from SPICE, and the yellow dotted dashed line is the predicted pulse from the machine learning model. As you can see, it is very accurate, and it has a very small error, and the average error from our experiments is around 3%. So what's next in our research activities? First, we are planning on doing some irradiation test campaigns, and specifically TID and SCQ testing of aging monitors developed by IHP. We also plan on irradiating with neutrons a synchronous and an asynchronous network on chip. Then we also have started working on aging analysis, and here we are going to perform parametric SPICE simulations, and we are going to use again here the aging sensors of IHP, and we are planning on implementing aging-based STA and aging-based SCT analysis. Also, we are planning to reconfigure the dynamic neural networks in order to detect the fault, and then reconfigure them in order to minimize the output error. And finally, all of these methodologies will be integrated into the EDA tool flow that I described earlier. So, in conclusion, the project started 12 months ago. Our mission is to perform research and innovation for integrated circuits for critical systems in ionized environments. We are 12 partners, 23 researchers. We will have many more events in the future, so stay tuned for this. You can follow us on our media, social media. Here you can find the site, our LinkedIn, Instagram, X, and follow us also on our YouTube channel, in which we have some demos and courses that you can enjoy. So thank you for joining us today. Thank you for listening to me, and I'm open for some questions if we have time. I don't know if I exceeded my time limit.
Yeah, you are fine. We have 5 minutes, Nikos.
Right.
So if anyone wants to ask something about TWIN-RELECT project or any other question for Nikos? Have some comments in the chat. Okay.
Okay, we can move on, I guess, and we can discuss, and all of us, we can discuss in the
roundtable.
In the roundtable, yeah,
okay.
Right.
Okay. So let's move on to the next presentation. Professor Tatiana Nichols will present from University of Nice. Will present the project IDA for EDGE. Professor Nicholas, can you share your screen?
Okay, I will share my screen. Just a moment.
Yes.
Do you see my presentation?
Yes, perfect.
Oh, okay,
Thank you.
you.
You can start.
Okay, good morning, everyone. Today, my name is Tatiana Nikolic from Faculty of Electronic Engineering, Niš. And today I will talk about intelligent error detection in reliable electronics from classical redundancy to machine learning. Exploring how we move from classical redundancy-based mechanism to modern data-driven approaches using machine learning. During this presentation, I will first say something about AIDA for Edge project. After that, I will give an overview of classical redundancy-based error detection and describe how machine learning can complement or even supplement redundancy. Here you can see the most important information about the project whose name is Twinning for Excellence in Adaptive Edge AI. Project started 1st October 2024. Project duration is 36 months. What is our goal? The goal is to develop self-adaptive AI accelerators. Such systems can autonomously reconfigure their architecture and functionality. Self-adaptation allows for a trade-off between performance, inference, accuracy, power consumption, and reliability. The goal addresses three main topics: neural network models, neural network accelerators, and reliability of neural networks. When consider self-adaptation of neural network accelerator for edge applications, we include three domains: precision, structure or function, and reliability. Motivation for applying reliability enhancement techniques can be found in complex computer systems that are all around us. In such systems, every large piece of hardware or software is prone to bugs. It is known that even the space shuttle have flown with potentially serious bugs. We can say no matter how robust design is, 100% fault-free design is impossible. Designers use different techniques to reduce the number of faults in systems. However, that is not enough. It is necessary to build systems that will recognize the existing fault in incorporating the technique to tolerate these faults or isolate the defect models. Such systems should still deliver an acceptable level of service. To achieve the needed reliability and availability, we need fault-tolerant systems. To have ability to tolerate fault by detecting failures and isolate defect models so that the rest of system can operate correctly. The main challenges for designers of complex system on chip are the following: increasing the IP core's chip's functionality, providing efficient data transfer with reduced number of wires, decreasing power consumption and enhancing reliability with as low as possible area and time overhead. System reliability refers to ability of system to function correctly over time, especially in adverse conditions. It includes concepts like fault tolerance, fault detection, recovery time, and ability to anticipate failures before they happen. Reliability has always been a key requirement in electronic systems, but its importance is growing as our devices become smaller, faster, and more complex. Miniaturization makes components more sensitive to soft errors, defined as bit flips caused by radiation or electronic noise. Therefore, to increase system reliability, it is necessary to consider both computation-based and communication-based aspects of the design. Many modern systems operate in safety critical domains where a single undetected fault can have serious consequences. In such safety critical and high reliability electronic systems, error detection and fault tolerance are foundational. Traditional design techniques can't easily keep up with this level of complexity, and that's where intelligent fault detection becomes essential. Traditional fault detection and fault tolerant methods rely heavily on redundancy, hardware multiplication, adding voting logic, using error correcting codes. But as systems become more complex, miniaturized, power constrained, and with more intelligence at the edge, we need more flexible, intelligent approaches. Form of redundancy, traditional form of redundancy are hardware, software, information, and time redundancy. We will briefly consider some of the many known resilient structures that incorporate redundant components. An M of N system consists of N modules and water and needs at least M of N for proper operation. The best known example of this type of system is triplex or triple modular redundancy, where three identical modules perform the same operation and the voter decides the majority result. Duplex system is the simplest example of module redundancy. Duplex system consists of two hardware modules and the comparator. Both modules execute the same task. If comparator finds that the module outputs are in agreement, the result is assumed to be correct. Simple forms include error detecting and error correcting codes that add redundant information to detect or correct bit errors in memory or communication links. The benefits of redundancy are well known: fault masking, detecting behavior, and well understood analysis of failure modes. These methods are robust and well understood. However, they come with significant costs, such as additional silicon area, higher power consumption, and scalability limitations. Moreover, classical redundancy detects or masks faults, but does not predict them. It reacts after a failure occurs. Also, as electronic systems scale down and systems become dynamic, reconfigurable, static redundancy becomes less efficient and less adaptable. If the question is why move beyond classical redundancy, several answers can be given. There are several motivating factors. Complexity and the variability of modern electronics, multiple interacting subsystems, heterogeneous hardware, many cores, dynamically reconfigured systems. Other factors, power and resource constraints. Duplicating large subsystems may be infeasible in edge devices, needed for early fault detection rather than just masking. Redundancy mask faults, but after they occur. We want proactive detection, prediction, remaining life estimation. And the most significant factor is data availability. Today, we have more and more sensors and devices connected via IoT, which enables the collection of large amount of data. Therefore, combining classical redundancy with intelligent error detection methods such as machine learning is increasingly attractive. Classic redundancy can be supplemented with intelligence because now we have data we didn't have before. This is answer to questions why now machine learning. In recent years, we have seen a paradigm shift from static rule-based reliability mechanism toward data-driven and intelligent approaches. Modern system continuously generates a large amount of data. These data streams can be used to train machine learning models that learn what normal system behavior looks like and then detect deviation on anomalies that indicate a fault. Machine learning brings a new dimension. Instead of simply duplicating hardware and voting, we can monitor system behavior, sensor outputs, internal signals, and learn patterns of normal and faulty. Machine learning enables system to learn from data. This means that they can detect patterns that indicate possible failures, recognize normal behavior, and adapt dynamically. Machine learning is a set of methods that can detect patterns in data and then use discovered pattern to predict future data or to make other decisions under uncertainty. The key advantages of machine learning is the contents is the following. Enable predictive diagnosis before failure occur. Machine learning methods can identify signals or patterns that indicate independent failure, enabling proactive maintenance. Facilitates adaptive control strategy after failure. And reduce need for full hardware redundancy, saving space and power. This figure presents the broader picture of how machine learning contributes not only to fault detection, but also to prediction and prevention. Here, data from sensors, controllers, and electronic modules flow through layers of data acquisition, feature extraction and machine learning based analysis, enabling system to predict fault before they manifest. In this approach, machine learning acts as a cognitive layer of reliability, learning from historical and real-time data to estimate the system health, degradation trends, and potential failure points. Machine learning can be used across the entire system life cycle. During design time, to simulate and predict failure scenarios using collected data. This is shown in the upper part of the image. During runtime for real-time anomaly detection, adaptive control, and error correction. This is shown at the bottom of the image. Here, machine learning can be used for post-analysis to analyze logs and retrain models for future fault prevention. In machine learning, we have paired variables, an output of interest y and vector of features x. Understanding the different categories of machine learning is in relation to this equation, y equal function of x. Model is what is learned from the data. Y prime is equal function prime of x. Learned model approximates the unknown function, enabling system to make predictions on uncover hidden patterns. Here we can see different categories of machine learning for a given task, which depends on the type of available data and the type of question asked to understand it. Based on available data and the task at hand, we select machine learning methods. We can use supervised learning. This is method which uses labeled data to model the relationship between input and outputs. Also, we can use unsupervised learning, which analyzes unlabeled data to uncover patterns, and reinforcement learning, which enables system to learn optimal actions through trial and errors. Here we can see a comparison of models belonging to different types of machine learning. Depending on our needs and the characteristics of the machine learning method, we decide on particular options. In addition to many advantages, there are also disadvantages to implementing machine learning models. Challenges for machine learning are data needs, computation requirements, and complexity of integrations. Here we can see commonly used machine learning models, which apply to increase system reliability. We can see where each model is used and what is its advantages and disadvantages. For example, regression model, support vector regression, is used in edge AI due to accuracy and low resource usage. Classification models are used for fault detection and state classification. Autoencoders learn model system behavior and detect deviations. These models are often integrated into embedded systems, FPGA SOCs, to monitor, detect anomalies, and trigger safety mechanism. Now the question is which model is best? Given the large number of supervised and unsupervised machine learning models available, it is fair to ask which one is better or best. The answer is this: no model is universally better than any other algorithm in all applications. In other words, all models are created equal and their performance is similar when averaged over all possible applications. This absence of a universally better or best model may be initially disappointing. However, it provides great opportunities for research and use of machine learning in different applications. This influences the research of different models and the adaptation of research to particular application. Which model is better or best depends on the specific application under consider. Here we can see architecture for machine learning-based error detection. Machine learning-based fault detection framework operates in two main parts: a learning phase or training and validation phase, and implementation phase. In the learning or offline phase, the system learns what normal and faulty states look like. The first step is data acquisition. Next step is processing and future extraction. Next step is model training and validation, and the last steps is model selection and export. In deployment phase or online phase, the system uses already trained model for tracking and detecting errors in real time. The key idea in our project is to build machine learning-based checkers that continuously observe characteristic signal patterns within different parts of system and identify deviation that may indicate faults. To make this approach scalable, we start by dividing the complex system into smaller modules, for example, 2 or 3 functional blocks that communicate through well-defined interfaces. Within this modular framework, we can observe and analyze several groups of signals: input signals, which present external data or control inputs entering the system, intermodule signals, which present data exchange between 2 or more modules, and output signals, which present final results on control responses leaving the system. Our goal is to generalize the machine learning-based checker concept from specific checker to modular system-level machine learning-based monitoring framework. Once the data set is available, machine learning algorithm can be trained to recognize the boundary between normal and anomaly or faulty behavior. During runtime, trained model acts as checker. It receives the live signal observation and classifies them as either healthy or faulty. When potential fault is detected, the checker can trigger an alert or invoke recovery mechanisms such as reconfiguration. Machine learning-based checker operates in 2 phases, learning and deployment. In the training phase, data are collected from sensor or internal registers and used to train and validate a machine learning model capable of distinguishing normal from faulty behavior. When the model is optimized, it is deployed to the target hardware. Machine learning checkers do not require full duplication of hardware module, thus reducing area and power overhead compared to classical redundancy technique like TMR and DMR. This slide presents a machine learning-based error detection system for reliable operation of a functional model. This is one proposal of machine learning-based error detection system. The function model represents part of an embedded system or even entire system implemented a system on chip or on FPGA platform. This system model executes any functions, exponential or logarithmic function. The proposed system consists of two independent hardware modules, traditional computation model, which calculate the target function using predefined mathematical algorithm, and machine learning-based model, which uses pre-trained model to approximate the same function. During runtime, both modules operate in parallel, receiving identical input values and producing corresponding output. Dedicated comparator unit continuously monitor the output and identify any disagreement between the two results. The goal of our research is to develop a machine learning model capable of accurately approximating nonlinear functions such as exponential and logarithmic function. Given that this task involves learning mapping from known inputs to known outputs, it is indicated as supervised learning model. Since the output to be predicted are continuously numerical values, the appropriate machine learning approach is regression. Regression models are specifically designed to estimate continuous output and can vary in complexity based on functional relationship between input and output. To evaluate the suitability of different machine learning models for approximating mathematical function within system blocks, a series of experiments are conducted. The focus is on two commonly encountered nonlinear functions, exponential and logarithmic functions. Since regression is the most appropriate approach for approximating continuous function, several regression-based models were analyzed: linear regression, polynomial regression, multi-layer perceptron regression, and support vector regression. A comparison of the results is shown in this table. Among the evaluated model, polynomial regression consistently demonstrated high accuracy with low complexity, making it practical choice for approximating both exponential and logarithmic functions. MLP regression provided competitive performance, but at the cost of significantly increased complexity. Support vector regression achieved the best result for logarithmic approximation, but require careful tuning and may not generalize weight to all function types. This finding highlights the importance of considering both accuracy and model complexity when selecting machine learning model for function approximation in embedded or adaptive control systems. Let us summarize some trade-off and challenges when shifting from classical redundancy to machine learning error detection and how to mitigate them. For example, computational resources. Embedded system may have limited resources, and in addition, two machine learning models may require computation. In this case, lightweight models edge machine learning optimization, quantization, pruning can be used. Model drift and aging is a challenge also. Online learning, periodic retraining, drift detection can be used in this case. Integration with redundancy can be used also. In this case, architecture must support safe fallback mechanisms. Robustness to fault in machine learning itself is crucial. The machine learning model and its hardware must also be resilient. And the end, explainability and trust. We can ask, can we rely on a machine learning model to make safety critical decision about faults? Unlike deterministic logic, machine learning models are statistical. In the end, we can conclude classical redundancy techniques remain the foundation of reliable electronics, but as systems become more complex and resource constrained, they need adaptive mechanisms that go beyond static duplication. Machine learning offers promising capability to detect fault early, adapt to changing behavior, and reduce hardware cost. The best strategy is hybrid, using redundancy as baseline safely and machine learning as intelligent overlay for detection. But machine learning brings its own reliability challenges: data drift, model robustness, verification, resource constraints. As electronics continue to become more complex, autonomous and connected, moving to intelligent error detection architectures is increasingly necessary. Thank you for your attention.
Thank you very much, Professor, for your presentation. Are there any questions from the audience? I don't see any question. Okay, so thank you very much again. And now I think it's time for our break of about 10 minutes. So be right back 10 minutes to continue with our next presentation. Okay, I think it's time to move on to our next presenter, Professor George Floros from the Trinity College Dublin, who's going to present the Coin3D project. So, George,
Yes, let me
can
share
you
you my
share?
screen.
Yeah.
Can you see my screen?
Yes, yes.
Perfect. So thanks, Akis, and thanks all the TWIN-RELECT team for organizing this webinar and inviting us. I'm going to give you a brief overview of the Coin3D project, which stands for Collaborative Innovation in 3D VLSI Reliability. So we target a bit more the 3D aspect of VLSI, and why we do that, because, starting from, let's say, give you a brief overview of our consortium and our partners. So Coin3D is coordinated by University of Thessaly, by the same department actually as TWIN-RELECT is being coordinating from the Electrical and Computer Engineering department. And we have U Bremen, which has a very high expertise on physical design methodologies for 3D ICs. We have University of Amsterdam, which is have also a good expertise in system level design approaches, and University of Glasgow, which has a very good expertise in machine learning and data management approaches, which are essential for our project. So there are 4 partners which are very complementary between them, and we try to produce some results, training events, and material. And why it's now important? Because there has never been a better time for semiconductor until the recent days. So if we see the ecosystem of semiconductor, we can see that there are now, as also the previous speaker said, an expanding range of applications. So we need more silicon. There are processor everywhere with the Internet of Things adoption. We have processor on cars, automotive, television, in critical infrastructure industry, actually everywhere. As a result, we need, of course, more R&D. We need more innovation. Or at this moment, we need. We have gone far beyond the more than Moore trend. So we need actually emerging architecture, emerging devices, and emerging materials, because we cannot now produce more area, more power, and more performance in a single actually chip design. And of course, oops, sorry. And of course, at the moment, there is also an increased revenue in semiconductor design. So the idea is to participate in this training, in this cycle, so to have also more training material, more open source tool, which lead to more R&D, lower cost function, and as we said, more applications for semiconductors. And why reliability? Because reliability has become actually a real world challenge. So we have gone far, beginning from system in package back in 1998. We have integrated RF modules on top of that. We begin to have integrated 2.5D chips around 2010. While from 2018, we go to bumbless 3D ICs. Now we're in the heterogeneous. We try to integrate different photonics and go far to monolithic 3D IC. And of course, designing a chip like that, designing monolithic 3D ICs or in general 3D ICs, it's a very complex task, because it involves several problems and several abstraction levels. So in order to sign off your chip in these methodologies, you need several solver technologies like method of moments, finite element methods, boundary element methods, different like fine difference methods. You have to take into account different problems which are very hard to solve, like electromagnetic interference, circuit and power analysis of the circuit, the heat transfer. You have fluid dynamics and solid mechanics, so you have a bunch of multi-physics problems which are very hard to solve. And of course, you have to solve all of them in different aspects. So you have to take into account into chip or chiplet level as a package, or even as a PCB in order to produce the final system. So it's actually a very hard problem. It's to solve. There are a lot of interplay phenomena among the different abstraction level and different technologies that are involved. So in Coin3D, we have tried to tackle several scientific activities, and in particular, we work a lot in the circuit level. So we have created an open source methodology for 3D IC design, which I'll give you some details on the topic, which actually is going to be presented next week in HCCC conference. We create machine learning methodologies for optimizing interconnects in 2.5D and 3D, and especially in power delivery networks. And we try to provide reliability analysis and assessment in 3D chiplets. Also, for the system level, we try to tackle also to see the system more holistically in a higher abstraction level in order to integrate more phenomena and see how it actually can simulate the whole system with actual workloads. So we have created the hot proton tool, which is actually a thermal aware electromigration framework taking into account realistic workloads, realistic processor setups, and all of them integrated also physics-based models. So we try to also implement now schedulers for 3D system level simulation, try to model in this abstraction software and hardware modeling, and actually give back to the physical level macro models for the 3D stacking. And of course, in order to implement all of this, we have several cross-layer methodologies like numerical and model order reduction methods, machine and deep learning methodologies, and several processing models for the 3D stacked architecture that they're actually integrated across all aspects of the abstraction level that we're looking on. So for, let's say, physical level methodologies, what we have tried to do in the first year, actually the project is running a bit more than 1 year. So we have an open source 3D physical design methodology. So it's built upon the open road infrastructure. It's completely open source. It supports different configurations like face-to-face, face-to-back, monolithic, and hybrid architectures. It provides an hierarchical 3D place and route with multi-PDK support. I'm not sure why this is happening. Really sorry for that. Okay, let me. Okay. And extend the left, def, and liberty files for tire-aware design. And also we try to work also on the electromigration-aware design based on the coherent diffusion equation model, which is a physics-based model. And if you look that electromigration has been identified as of the most serious concern in future IC designs. So we try to use numerical solvers and gradient optimization. We have implemented some machine learning prediction with gradient boosting for early electromigration hotspot detection. And we try to use hybrid physical and machine learning modeling for speed and precision. So to give you a bit overview on the physical approaches, The 30PDX framework, it's actually open source. You can also visit our GitHub in the project and download the scripts and all the infrastructure. So it's the first fully open source framework for hierarchical design exploration. It's built for that. It's not for sign-off purposes at the moment. It's more on the design space exploration. And what we try to do, we try to have different PDKs. We try to have a script for the user preferences, and then we create a set of 3D collaterals. We use the floor plan, and we try to, for all the different cores, to do placement in the different tires, do the clock tree synthesis and timing optimization. I think, okay. And if you see the result, so we can have different, it can provide different 2D and 3D implementation and take all the different results like power, area constraints, and see the different reports. Now, moving beyond that, we try to integrate also reliability models. That the idea is to have them all them together in a complete framework, where we at the moment integrated some AI-based models for early prediction of degradation. And the idea is to find the compact features. So what are the most important features that they impact electromigration aspect? So we have identified the current density, the temperature, and the diffusion parameters, and we try to give a concrete methodology based on the XGBoost. Actually, if you consider a power grid line, like the one that you can see on my screen on the left bottom part, so you see that there are a lot of metal and wires and different parts where are the segments start and end. So we have created actually a methodology that it can extract the features and it can implement it in conjunction with different machine learning or deep learning methodologies. So we have actually employed this special and relation of the points and the atomic diffusivity to create data sets that we're going to publish also open source based on the IBM benchmarks and have the feature extraction and do the online prediction. Also, I think, sorry, we have created a system-aware PDN power delivery network generation, so it can take into account the dynamic power-aware PDN synthesis for workload traces. It optimizes power grid and pad allocation for airdrop and electromigration limits, while we have worked also creating a complete tool for thermal-aware reliability framework. So in order to couple the simulation with established architectural simulation tools like Hot Sniper and Comment, to have cross-layer modeling that connects workload, thermal and aging effects, and enable runtime feedback between architecture and the reliability engine. So how we do all this stuff? So we have this Hot Proton tool that we're going also to publish and make it open source also for the academic community. So I'm sorry for that again. So the idea of Hot Proton is it's the first framework that tightly couples architectural level simulation with physics-based EM stress analysis. And how actually it works, this is the complete idea of Hot Proton. So it can take a floor plan based on Hot Sniper or the Comet tool, that they're architectural exploration tools for 2D and 3D respectively. It can take a power model based on the MacPad and the thermal model actually based on the hotspot. So the first idea is to create the power grid. So if you have given a floor plan where you have the different parts of your core, you have the FPU, you have your ALU, your memory stuff, your different instruction set, buffers, and actually whatever you have in your model. Then by getting a first simulation, you can actually create a power grid. So the idea is to connect your floor plan with your power grid and attach some, let's say, pads that give power to the system. Once this is formulated, then we use physics-based model based on Proton tool, which is again an open source tool that were published from our group in the previous year. And we try to calculate the time to failure of the entire system and to map the different time to failures to subcore and see the reliability values of the different cores and subcores. And we try to, let's say, print out the different heat maps, the thermal traces, the power traces, along with the stress values and the R values of the system. So this is actually a complete framework that also integrates physics-based, which is very important at the point that the industry is at the moment. Most of the tools use most heuristic methodologies which are not so well, let's say, defined. And of course, closing my presentation, all these activities, all the scientific activities are coupled with different training activities, with research and knowledge exchange in the area of 3D VLSI. So we plan to organize different workshops and special sessions. We have a visiting researcher program for University of Thessaly to other outwork institutes that they are part of consortium. We have 3 summer schools, 3 webinars, and 3 advanced training courses that they are actually up and running. We try to organize early stage forums here or actually or abroad in order to bring earlier stages together and discuss about their ideas and how they can formulate groups together. And of course, we try to produce some ideas how we can assist researchers in translating the research outcomes into actually commercial ventures and foster this network of collaboration and knowledge exchange. So I would like to thank you all. Sorry for the problems with my teams today. At some point, it was keep failing. So if you have any questions or something that you want to discuss. Yes, Nikos.
Hi, George. Thanks for the great presentation. I have a question about the open sourcing. So you mentioned about this creation of the 3D library.
Mm-hmm.
And if I'm not wrong, this is already available in GitHub.
Exactly.
Okay. Are you planning to open sourcing the entire project, the entire code and the entire utilities of this project?
Actually, yes. I think all this project is open source, so all the different utilities, and we're now also in the process of extending, having, let's say, more advanced capabilities. So this was the first approach. So the 3DPX is actually available online and the entire project. And for us, this is the idea to what we try to produce, to have everything online and accessible.
Great job. Okay, thank you.
Any other question from the audience? No. Okay, George, thank you very much.
Yeah,
for
thank you.
being here for your presentation. So let's welcome the next presenter, Daniel Paul Soderstrom from CERN, who's going to present the project RADNEXT. So, Mr. Soderstrom, can you share your screen?
Yes, thank you. Let's see if I can share like this, perhaps.
Yes, okay.
Good. All right. So thank you for the invitation to present the RADNEXT project here. So my name is Daniel. I work at CERN in the R2E team, so the radiation to electronics team. I've been here for 2 years now as a postdoc equivalent position. So in this presentation, I will show a bit the topic of the RADNEXT project, the execution of it, how it has been implemented. We'll tell you about the participants in the project and some of the outcomes that we have had as well. And then I will look a little bit to the future as well, what we can expect from RADNEXT in the future. So RADNEXT stands for Radiation Facility Network for the Exploration of Effects for Industry and Research. So it focuses on the research and testing of radiation effects on electronics. This is done through transnational access provision, as well as joint research activities among the members of the consortium. And this TA is then mainly focused on single event effects or particle-induced effects, as opposed to, for instance, total ionizing dose effects. But this joint research activities include both of these types of effects. And I include here also a little bit introduction to radiation effects on electronics, just one sentence that this is about characterizing components and circuits and their reliability in radiation environments. And this can be, for instance, for space applications, aviation, ground, or for high energy particle accelerator applications as well. And the core of the RADNEXT project is to provide this transnational access to radiation infrastructures for users. So this need was identified in the previous project within a similar consortium called RADSAGA, where the organization of the research access for the students for radiation tests proved to be quite difficult because the beam time is scarce at facilities, and scientific beam time is you have to normally go through a committee at each and every irradiation facility that you are intending to test your component at, which can be difficult, or can be more or less smooth as well. But it could be long wait times, for instance, associated with this. So the RADNEXT then project provides an alternative path to this approach. So how does it work then with this transnational access? So you submit or create a proposal that is submitted through a specific online portal that we have in the project. And this submission has been open 1 year and 1 month duration 3 times per year. So normally January, May, and September. And anybody can create and submit this proposal who are interested in getting beam time. Then each of these proposals are reviewed by 3 reviewers, one from the work package leaders of the specific transnational access mode, one from the scientific advisory panel, and one from the industrial advisory panel that we have in the project. And then the proposal gets a score from each of the reviewer to be able to compare among each other. Then the accepted proposals are paired then with a suitable facility in the consortium, where the facility coordinator then in turn checks if the proposal is feasible from their end as well, and accept it if it is. Then a bit detached from the RADNEXT organization, the user and facility together, they coordinate the beam time, schedule it, and perform it when it's suitable for them. And then afterwards, the user writes a test report. This test report will be openly published on the Zenodo repository. And okay, if they use the results elsewhere, of course, they credit the EU contribution and the RADNEXT project and so on. And perhaps most importantly, the access to the facilities are funded through the project and from the EU. So it's free to the users to get this beam time. So here's a bit of a timeline to show where we are in the project. Okay, we are here, as we see, at the end of 2025. Close to 2026 and also close to the end of the project. Actually, we started in June 21 and we end last of May next year. So the proposal was submitted in 2020 and then it was we have had annual meetings, 4 of them so far. Next year will be the final wrap up of the project before the end. Also, we have had RADNEXT workshops through the project. So these have been quite popular in the research field for radiation effects on electronics, with quite many interesting presentations and good level of attendance as well. These have been in the same time and place as the annual meetings the past since last year, then to organize a bit easier. And then the beam provision, sort of a broad overview here. The first call for beam time proposals we had just after the start of the project. Then we delivered earlier this year up to 4,000 hours of beam time. And we had the last call for proposals in the project open during September, so it was recently closed as well. To show a bit then the consortium, the coordinator is CERN, and then the different facilities. It's quite many. I will introduce them in the coming slides a bit more. And the academic parts of the consortium are Montpellier, KU11, Padova University, Université Jean-Monnet in Saint-Étienne in France, Oldenburg University, University Carlos III in Madrid, ISAE Supaero, and Paris Mines as well. We also have agencies and institutes as partners. These are CNES, DLR, INTA, and Fraunhofer, as well as some industrial partners in the form of Airbus, 3D Plus, IROC, Alter, and Datsman, Interact and Innovate. So the facilities in the project, they span essentially the major radiation facilities in Europe, providing various types of beams, heavy ions, protons, neutron beams, and as well as a few more different exotic types of radiation fields as well. So looking first at the heavy ion facilities in the project, we have JYU, University in Finland, UMCG from Netherlands, UCL, Ganil, GSI, and CERN. These are composed by maybe 2 different categories based on their acceleration types, synchrotrons and cyclotrons. If you're not familiar, then don't worry. But the synchrotron facilities of GSI and CERN, they are shown here in this figure. So they can provide essentially quite high range of energies with ions, which is important for instance, what we heard about in the last presentation. If you have a thick 3D structured components you want to test, then you need to have high energies and long ranges of the particles that can penetrate actually through the device, which is not the case maybe for the lower energy facilities. But if you don't need a high energy, then the lower energy are quite good, because they are normally versatile in terms of the linear energy transfer, so the amount of energy that they can deposit in the device per ion. So normally you want to characterize the device as a function of LET, then going from small to high values. So yeah, it's they complement each other quite well, these different types of facilities. In terms of protons, we have UMCG, HPTC, CNA, PSI, HCDR, NPI-CAS, and also TRIUMPH in Canada, where we have different types of accelerators again. For instance, these medical cyclotrons, the orange dots here. These are facilities where normally you use the proton beams for proton therapy, so that you would during normal working days, you have patient treatments there, and then in the evenings, nights, and weekends, you can use the beams for component testing and research instead. So then, these different types of facilities can be used for a few different types of testing. High energies maybe for normal single event effect testing, with lower energies maybe more for either direct ionization SEs or displacement damage tests or detector tests or such. Then there are also two facilities that are a bit special with the laser-driven, laser plasma accelerated protons. So HCDR and now see CLPU is in Spain here. It's not on the map, but these are providing a bit different types of beams with a spectrum of energies instead of single energies that you would get on the other accelerators. In terms of the neutron beams, it's a quite wide range as well, as shown on the map here, with a few different types of beams. So we have atmospheric neutron spectra, monoenergetic neutron spectra or beams, and other neutron spectra as well. Where these atmospheric ones are of interest maybe for ground applications or aviation applications, where you have a particle spectrum from the beam that is mimicking the one that is found naturally in the atmosphere, so that you can directly correlate the response in the beam to what would happen with the component or the circuit in use in its application environment as well. Then in terms of the other beams, you have electron beams and electron Bremsstrahlung photons at HCDR. So this Bremsstrahlung is when the electrons are stopped in a heavy target, for instance, they are converted into a photon beam that can be used for irradiation as well. At CERN, we have also this CHARM, the mixed field irradiation facility, which is a large radiation field that you can put big systems to test in. It's a field that is relevant mainly for the accelerator environment around CERN in LHC, for instance. But also there has been irradiation of, for instance, a CubeSat there as well for testing for radiation effects. In the UK, at the same place as it was also the atmospheric neutron beam, GPIR, you have also a muon beam at the same facility. At GSI, apart from the synchrotron, they have also its heavy ion microbeam facility with a heavy ion beam with a micrometer spot size that you can directly target certain parts of your device to investigate local effects. And also ESRF, a synchrotron light beam line in Grenoble here, where it delivers short pulses of X-rays of high intensity. Then the types of beams that have been requested by the users, they vary quite a bit. So the final call for proposals, as I said, has just been completed, and in total we have gotten 485 proposals for beam time. As we see in this graph, it's mainly heavy ions and protons that has been requested. Also, then the neutron beams are a bit below, and then you have the mixed field and other types of beams as well. In terms of the transnational access that we have delivered, then out of these 485 proposals, 237 has been accepted. This does not include the recent call. Hopefully, we will send out the acceptance notifications to the users in the coming days from this. And then 172 of them has been completed so far. And in the right plot here, you see the beam time hours. So 5,300 hours have been assigned before call 15 again, and over 4,400 hours have been delivered now to date, where we are now. About the users then, based on the PIs of the proposals, or the principal investigators of the proposals, we have had 130 from industry, about 1/3. 13% have been proposals with a female PI. And in terms of the countries, mainly they come from the large countries in Europe, as we see in this table here. But also we have users from USA, Brazil, South Korea as well, that have sent proposals to us. And then here we see the distribution among different fields of research that the users come from, or the users institute are part of. Yeah, and in terms of the output of the project, we have had a lot of, or 11 RADNEXT webinars so far. They have been recorded and put on our YouTube channel page here. So if you want to know more about certain facilities or yeah, something specific that we have had a webinar about, you can check out the channel, and it contains a lot of interesting information. There's also a book under preparation, which will be collecting the research that is done and information that is collected in the various deliverables that we've had in the project. So it's envisioned to be an overview of the radiation testing on electronics procedures, from the fundamental concepts up to more advanced methodologies developed recently now in the RADNEXT project. In terms of research activities, these 4 work packages have been the main main JRA work packages. So in work package 5, there were research done in dosimetry solutions for facilities with some innovative instrumentation and detector developments. Work package 6 focused on the standardization of methodologies and system level testing procedures and system level qualification procedures. While the work package 7 worked with cumulative radiation effects, so this is total ionizing dose and total non-ionizing dose, including testing procedures using X-rays instead of cobalt-60 based gammas. That is maybe the most standard way to do it, as well as TNID, or displacement damage effects in image sensors. And work package 8, we're focusing on modeling tools for radiation effects. So that included work on or with FLUCA, GEANT4, GA4 SE, ACORS, and SPICE, to name a few. And the research output from these work packages have been, from what I can see, at least over 40 papers of the direct result of the research done within RADNEXT. And of course, the workforce development is a big part. Of course, more than 10 students and early stage researchers have worked in the project. Yeah, and many more have contributed more peripherally, of course. There are a few faces to represent these. Then also we have had these test reports that I mentioned. 138 of those so far have been published openly on the Zenodo repository. And then looking a bit towards the future, so the current RADNEXT project ends in May, end of May next year, as I mentioned. But then after this, we hope that there will be a continuation in the form of RADNEXT 2030, which would be then spanning from just after the end of RADNEXT until 2030, so a 4-year duration project. So we sent the proposal now during this autumn, and we hope we will probably get the reply then early next year. So we hope it's a positive one, so we can continue the work. And that will be also centered around beam provision through transnational access as well. But this time we will include a bit more facilities, for instance, for total ionizing dose testing, so some cobalt-60 facilities and such. And there will be SE laser testing facilities, and we will essentially more or less double the amount of facilities and irradiation opportunities to the next project. with mainly the European ones shown here on this map, but also Canada and Triumph will be represented again, but also Ansto from Australia will be part of the project if it's accepted. And to summarize, we have delivered more than 4,400 hours of beam time to 172 user groups so far. I have to deliver the rest until May next year, so half year left. We have provided access to irradiation infrastructure for with a lower threshold than has been previously available. For instance, for small companies, but also to plenty of more established universities and agencies, research centers and such. Many research activities have been completed in the fields of dosimetry, system level testing, cumulative effects testing, to name a few. And then for the future, we hope that our legacy then will be continued in the RADNEXT 2030 project, hopefully next year already. And okay, this is the members of the consortium again. And then I will leave you with some links here, useful links to keep in mind. And I thank you for the attention.
Thank you very much for your interesting presentation. Are there any questions from the audience? Yes, Nikos?
Hi, Mr. Soderstrom. Thanks for the presentation. You mentioned about the availability of this infrastructure to SMEs and other groups, universities, and etc.
Yep.
Can you elaborate more about the process that somebody can use these facilities? Which is the main process to test a chip?
Yeah, so within RADNEXT, if RADNEXT 2030, for instance, get accepted, then you can apply, or anybody can apply using these forms through the portal mentioned there. So there you would have write a proposal which contains the project excellence, the implementation status, and also the impact of the research that you want to do. And then, going through the process that I mentioned on this slide earlier. But then if you want to go directly to a facility, you can, to most of these facilities, they have paid access for industry that you can contact the facility and say, okay, I want this number of hours of beam time. And then you have to wait until a free slot appears and then you pay for the access. Otherwise, you send a proposal to these committees that normally their different institutes have. That then probably maybe twice per year, I think is a common. They will have a meeting and then they decide which of the proposals that they have gotten that they will grant beam time to. And that probably takes then a longer, is a longer process, but then, okay, it's for science, so that will be free then. So it depends on the mode of access that you want to use. Hope this answers the questions. Otherwise, maybe if you have specific further questions, let me know.
I see. And can you provide a range of the fees?
Yeah, it varies quite a lot depending on the facility, and in ballpark normally could be around 1,000 euros per hour for the particle irradiation facilities, like the heavy ion beams, for instance, with the cyclotron beams with a bit lower energy. The ones with a bit higher energy are a few thousand per hour euros. Then for TID, it's quite much cheaper if you want to have total ionizing dose tests or facilities with maybe lower energies. That will be a bit cheaper, a few hundred maybe per hour instead.
Okay, thank you. Thank you so much.
You're welcome.
Any other question? I would like to ask something. Since there is a large number of proposals requesting various experiments for various beams, can you give us an estimation of the time that the project needs to wait, let's say, in the queue? Or is it a fast process, let's say, to book the experiments?
So within RADNEXT, normally from the proposal, it will be done within, I don't know, maybe from around 6 months. It's quite common from the proposal to the experiment. Without RADNEXT, I think with paid access, this can be the same. Yeah, maybe a couple of months of wait time, depending on the facility and the test you want to do. But that would be common, I think. And otherwise, with this, if you provide a research proposal to an institution to do it there, then it can take a bit longer, I think. But okay, maybe not more than maybe say 1 year or 1.5 years, maybe, I don't know, something like this. Depends very much on the place that you are looking at also.
Okay, thank you very much.
Thanks a lot.
So thanks again, Mr. Soderstrom, for his presentation. And let's move on to the next speaker, who is Professor Milos Marianovic from the University of Nice, who is going to present the RESIST project. Okay, so Professor Marianovic, we can see your screen.
Hello now. Can you hear me now?
Yes.
Hello.
Thank you.
Hello again. My name is Milos Marianovic. I'm assistant professor at the Faculty of Electronic Engineering from the University of Nice, from the Department of Microelectronics. And today I will introduce you to RESIST project. So in next few slides. So the full name of our project is Cross-Layer Reliability Assessment of Electronic Systems, or in acronym RESIST. This project is realized between two partners. It's, let's say, one small project, 1 year project. The partners are EHP, Leibniz Institute for High Performance Microelectronics from Frankfurt-Oder in Germany, and our Faculty of Electronic Engineering from the University of Niš in Serbia. The coordinators of the project are Dr. Marko Anđelković from EHP and Professor Dr. Daniel Danković from the Faculty of Electronic Engineering from Niš. So at the beginning of this project, we start with, let's say, 4 objectives of our project to establish a sustainable collaboration between these two institutions in the field of cross-layer reliability assessment of electronic systems. Then to initiate joint research on cross-layer characterization and modeling of the fault effects in electronic devices, circuits, and systems. We have our background in this kind of characterization of electronic devices, and now we want to have wider area to facilitate, also to prepare at least one joint research project proposal in collaboration with complementary academic and industry partners, and finally to define, let's say, a strategy for long-term joint research collaboration that focus on joint strategy that will be on identifying common topics for future joint research and to exchange and training of early stage researchers. This project is funded by DFG, that is a German research foundation. As I said, it's 1 year project. And now I will show you some of our activities during this 1 year. We start with this project in February this year with visit of our team to EHP. It was the first Thai chip winter school at EHP. We met each other then at EHP in Frankfurt-Oder. So it was the training school about reliable hardware infrastructure for upcoming AI chips. And here you can see our team, Professor Danković, who leads these projects from our side, and also colleagues from the AIDA for Edge project. You learn more about this project from Professor Tatjana Nikolić, also from our faculty. After that, I stayed there for 1 month. So we realized 1 month visit to AHP from February to the beginning of March this year. So then we start with our joint research with the AHP team. And in this presentation, I will show you of some of our results. After that, the colleagues from Germany visit us here. We organize seminar talk at our faculty. Here you can recognize Professor Dr. Fabian Vargas. He talk here for our students on-chip aging sensor score for silicon life cycle management. And then we organized at our faculty in May this year, first resist workshop. We organized this event with 35 participants. They give the invited talks on area of reliability, and we also organize poster section and forum on this area of science. We organized this first resist workshop with support. It is supported by also IEEE Serbian Montenegro section, IEEE Electron Device and Solid State Chapter Society, our student branch in Niš, and Women in Engineering Affinity Group, and of course, Twinning for Excellence in Adaptive Edge AI project, AIDA Edge project. Here, one photo from this event. So the first resist workshop is organized at our faculty. After that, we organized the second resist workshop. It was organized in June and July this year in Germany at the HP. So at this workshop, we have opportunity to learn more from 13 speakers, different papers, and to visit the clean room. That is a good opportunity for the team from Faculty of Electronic Engineering. One photo from this session of workshop. And as I said, one of our goals is to prepare some joint project proposal. Here you can see we look for the results. So we prepare one joint proposal. The acronym will be maybe SMART IC, towards a sustainable multidisciplinary education, research, innovation, a network for resilient integrated circuits. So we will wait for the results of this proposal. And as I said, we start with our joint research, and today I will show you some of our results. It was performance evaluation of digital multipliers for application in neural network accelerators. We presented these results at the International Conference on Microelectronics, IEEE MEAL. So after short introduction about the research motivation, I will show you some of the structure and characteristics of different kind of multipliers, array multipliers and Valence multipliers. Then I will show you our methodology for SPICE simulations, and finally I will show you some of the results of these simulations. So as we know, machine learning uses models to extract knowledge from data, and before that we use neural networks inspired by human brain, widely used in machine learning. We know for supervised and unsupervised learning, each input is paired with the corresponding output, and we have different methods like regression, classification. So regression predicts continuous values, classification assigns inputs to predefined categories. And for all of these methods, from linear regression to deep neural networks, computation are based on multiply accumulate operations. So we need MAC operations, which are computationally very intensive, especially in complex AI systems. And for that, we need systolic arrays. These systolic arrays are specialized hardware accelerators for neural networks. It is composed of processing elements and which are interconnected, and each processing elements include some adder and some multiplier inside, which operate in one clock cycle. Data flows synchronously through processing elements for efficient computation, and we need to optimize this kind of software. So our focus in this research is on performance analysis of various digital multipliers to understand power consumption and impact on neural networks performance of these kind of circuits. So multiplication is a core operation in digital and in machine learning hardware. And we can define latency, throughput area, design complexity. So these multipliers need to be optimized for latency or delay from the input to the valid output of data. Also for the numbers of multiplication per time and area on silicon, and of course, design complexity, and how to find, let's say, the good solution for multiplier. It's trade-off between speed, area, and of course, design. So in m times n bit multiplication, we need n partial products of n bits that need to be generated. For generation of partial products, we use AND gates, and then that products are shifted and summed to form the final m plus n bit output. And here you can see the, let's say, basic architecture of multipliers. School example, let's say, implements multiplication using shift and add methods. It consists of n times n grid of n gates. So to obtain all of these partial products here, we need some number of n gates for partial product generation, and then we need to sum up. For summation, we use full adders and half adders, and in for n times n multiplication, we need n times n minus 2 full adders and n half adders. So partial products are aligned with shifting through structured routing, so we don't need extra logic. And here you can see, of course, the full adder and half adder. So for instance, these partial products is the last significant bit P0, final product, but P1 bit is obtained like summation of these two partial products, and the carry out is fit to this full adder when we sum it with these two partial products to obtain the next sum, and then sum it in this half adder to obtain P2, and etc. So here you can see the structure of this circuit for 4 times 4 multiplication. So last significant bits product is P0, and higher bits are formed by combining partial product using full adders and half adders, as I said. So delays increase with array depth, of course. So we can define some advantages and disadvantages in this kind of circuit. Advantages are highly regular and compact layout of this kind of multiplier, and it is easy to design and to integrate it. On another side, some challenges are high latency and power consumption, especially for large word size. On the other side, we have Valence multipliers, which are optimized for speed by reducing addition stages. And the multiplication in this case consists in 3 main steps, let's say. Again, partial product generation, like at array multiplier. Then we have partial product grouping and reduction. As you can see here, all of these partial products are move up, and then we need to sum it in final addition step. For that final addition step, we can use different kind of adders. And here you can see the structure of Valence multiplier, for example, times 4 times multiplication. Here the delay is proportional to the logarithmic of n, where n is operand bit width. And of course, for this circuit also we can define advantages and disadvantages. So first of all, significantly faster when we compare with the array multiplier. And in this kind of circuit, we have parallel structure that minimize critical path. On the other side, some disadvantages are complex layout because of irregular structure of the circuit. And for final summation, we can replace these full and half adders with carry look ahead adders. So that algorithm accelerates addition by predicting carry bit in advance. As can we see here from this truth table, if A is equal to B and is equal to 1, so in these two cases, the carry out will be 1. And also, if we have A XOR B to be 1 and carry in is also 1, then the carry output will be 1. So based on that, we can generate carry out equation. It consists of two parts, carry generator and carry propagator. And here you can see the generalized form of this circuit. So in this case, when we use this kind of adder, we have significant speed up in carry computation. That reduce critical path delay in adders and multipliers, but on another side, we have increased hardware complexity because of this circuit. And here you can see the structure of Wallen's multiplier with carry look-ahead logic. So in our research, we use this tree structure to compare it. For that, we use cadence spectra. So we done a lot of SPI simulations. For that, we use 130 nanometers about CMOS technology from EHP, and in design, our design is based on standard cells library. So we created array and Wallen's multipliers. Wallen's multiplier is realized with and without carry look-ahead logic, and for the full adders and half adders, we realized our custom sub-circuits. And based on transient simulation, we obtained the propagation delay and power consumption of multipliers. So some of the results, here you can see the waveforms from the output. So the input is 1, 0, 1, 1, and the weight is W is 0, 1, 1, 0. So here you can see the expected output. And as you can see from this graph, because of gate delay, of course, product bits are not generated simultaneously. So the P0 is obtained after 100 picoseconds, and let's say most significant bit is after about 800 plus picoseconds. So this pattern of input is chosen because it's approximate worst case design, because most significant bit P7 is calculated in the same full adder. So we have minimal variation between these two delays in P6 and P7. And here you can see the results for propagation delay in function of power supply voltage for this technology of EHP. The nominal power supply voltage is 1.2 volts, and the minimum is at 0.8 volts. So as we can see here from this graph, Wallen's multiplier with carry look-ahead is only architecture operational at the minimum voltage. At the temperature, room temperature of 27 degrees, the fastest is Wallen's multiplier with CLA logic, and the slowest is array multiplier. Delay increase when, of course, power supply drops to 0.9 volts. We have, let's say, about 100% of increase in delay. And if we analyze what happened with temperature, then that impact is lower, so less than 10% in delay for all of the architectures. So at lower VDD, temperature influence is more significant. As you can see, it's more than 20%, it's up to 20% in propagation delay. Here you can see what happened with power consumption of multiplier for different power supply voltages and at different temperatures. So power consumption increases, as you can see, linearly with the supply voltage. Higher temperature leads to greater power consumption, of course, mainly because of leakage current increase. And here you can see the results for our investigated architecture. So Wallen's multiplier with CLA logic, then we obtained the highest power consumption, and the lowest is for Wallen's multiplier without carry look-ahead logic. Here you can see what happened with different driving strengths. For the design of our circuit, we use 3 different driving strengths, 0, 1, 0, X0, 1, and 2. Here we have increasing channel widths with from X0 to X2. So X2 is with the widest channel that leads to a lower resistance, but on another side the highest capacitance. So we just use standard cells, so no custom sizing here. And here you can see the propagation delay in function of power supply voltage. So the Valence multiplier with carry look ahead, it's with the lowest delay. With the smallest cells at nominal voltage, and delay increase up to 10% when we have wider channels of transistors, wider cells, let's say. And array multiplier, here you can see X1 cells increased 3.5% in delay when we compared with another ones. Here you can see the power consumption in function of power supply voltage at different driving strengths of our architecture. So power consumption rises with supply voltage for all of the architectures. X0 cells, the smallest one, consumes significantly less power. It's 2 times X2 cells. So it's up to 3 times lower. I want to say that. So the lowest power consumption is in Valence multiplier without CLA logic, where we use X0 cells, and the highest power consumption is for array multiplier and Valence with CLA logic, where we use X2 cells. So we obtain, as you can see here, the similar values for power consumption in function of power supply voltage. And to compare all of these data, we need some metrics. We decided to use PDP, power delay product. So lower PDP means better efficiency. And we evaluate all of these architectures of multipliers at the nominal power supply voltage of 1.2 volts at the room temperature, 27 degrees. So the best PDPs for Valence multiplier without CLA logic when we use the smallest cells. And the worst case is when we have designs with X2 cells, because of course, the highest power and delay leads to the highest value of PDP. Here at this line here, you can see the results for our, let's say, reference design from the literature. It is a realization for 90 nanometers. So if we compared here array multiplier with the X0 cells, in our case, outperforms 90 nanometers designs. Valence multipliers with X0 and X1 cells are better than 90 nanometers performance, and design with X2 cells, as you can see here, underperform compared to 90 nanometers design. And to sum up this, so in this research, you can see the comprehensive evaluation of array and Valence multipliers in 130 nanometers CMOS when we use SPICE models. At EHP, we estimate the results in supply voltage range from 0.8 to 1.2 volts, in wide temperature range from -40 to 125 degrees. And all of these architectures are analyzed with 3 different driving strengths. And here you can see the key findings. So delay increase with lower supply voltage, power consumption increase linearly with the voltage and temperature, driving strengths. We need trade-off when we talk about driving strength. So Valence multiplier without CLA logic with the smallest cells achieves the lowest PDP that outperforming prior 90 nanometers designs. And the similar results are for Valence multiplier with carry look ahead logic, but with the smaller cells. In our future research, we obtained some of the results, and we need to publish somewhere. So we will analyze approximate multipliers and the error trade-offs, and of course we do some simulations related with reliability, so with single event transient and then things how that affects these multipliers. So that is all from my side from about the RESIST project. So if you have some questions, I'm here. Listen.
Thank you very much, Professor. Are there any questions from the audience? Yes, Nikos?
Thanks, Professor, for the presentation. Actually, I have two questions. The first one is, how did you choose this type of multipliers? Of course, there are many different types of multipliers like Booth or others. The first one is this question, and the second one is that this analysis depends actually on the technology. So if we change the technology, do you believe that these results will remain the same? I mean, the trend will be the same, or it may be different, extremely different.
Okay, thanks, Nikos, for your question. So first, how we start with these, let's say, with these architectures, we decide to start from the basic one and then to choose different ones to compare the results. And related to your second question, yeah, I believe that the trends will be the same, but of course it depends not also on technology, but also depends on let's say, the number of bits at the input. Of course, the results of power consumption, for instance, of course, depends on the speed, on the input vector. So we need to do more investigation related with the let's say wider input bits, multipliers and that thing. So I believe that the trends will be the same if we talk about the power consumption, and when we talk about propagation delay and all other metrics related with multipliers. But of course, the absolute values will be different, of course.
Okay, thank you.
Thank you.
Any other question? Okay, I would like to ask something. If you can go to the plot, the slides with the plots for a delay, propagation delay versus temperature and voltage.
This one or for propagation delay?
This one.
Okay. Yeah.
Okay. If I'm not wrong, I noticed that there is a temperature inversion here. So there is no consistency in temperature increase after, let's say, 1 voltage. Have you figured out why does this happen? Or is it a problem of the library or something else?
Yeah, I think that it depends on technology. So I don't have opportunity to change nothing in the model, you know. So I just use the models from AHP, and here it's the obtained results. So of course, I think that also power supply voltage impact this temperature dependence. So yeah. I'm not sure why we have, for instance, here this kind of dependence, and here is, let's say, inverted, let's say.
Okay.
Yeah.
Okay.
Yeah, but yeah, good observation, and we need to explain this more.
Yeah, because we made some experiments and we have seen also this problem with HCCC.
Maybe we need to look for some physical things that happens inside. So maybe it's like
probably.
Yeah.
Okay, thank you.
Thank you.
So let's move on. Let's take a short break. Let's do this a 5-minute break. Okay. And we will continue with the next presentation. Okay, now let's continue with final presentation from Professor Ioannis Voyagis from the University of West Attica, who's going to present the Hellenic Chips Competence Center project. So, Professor Voyagis, can you share your screen?
Yes, good afternoon, everybody. Just give me a second.
Yeah.
Can you see my screen? It's okay?
Yeah.
Can you hear me?
Yeah.
Perfect. So, good afternoon from my side also. It's a great honor and happiness to be with you, having attended all the interesting presentations. The presentation has to do with the Hellenic Chip Competence Center. The credits for the presentation go to John Kikidis, who is the Executive Vice President of the Executive Board of the HCCC. So, a few words about the HCCC. It's a non-profit partnership dedicated to advancing the semiconductor ecosystem in Greece, aligned with the EU CHIPS Act. And its expertise spans microchip technology development, semiconductor fabrication, and embedded systems. Some of the key services include training, technology transfer, prototyping, and access to advanced design platforms. We target startups, SMEs, researchers, industry stakeholders, fostering collaboration across academia and industry. It spans all over Greece and collaborates with various national and international research institutions to enhance innovation and market competitiveness. Our vision and mission. Our vision is to position Greece as a key contributor to the European semiconductor industry, fostering innovation and nurturing high talent and promoting collaboration between industry, research, and academia. Our mission is to strengthen the value chains within electronic systems and components, particularly for startups and SMEs, by facilitating adoption and integration of semiconductor technologies. Our objective: to cultivate a fertile ground for innovation and nurture a skilled workforce specialized in high-tech domains such as analog, mixed signal, and RF components, photonic technologies, advanced sensors, embedded circuits, and low-power microprocessors for the IoT. We have founded by a dynamic innovation ecosystem, and we intend, to contribute significantly to the CHIPS Act outline goals. Our focus is to promote innovation in analog, mixed signal, RF, photonics, AI, sensor, and low-power chips, and to strengthen the workforce with upskilling and skilling programs. We offer access to advanced infrastructure and design platforms, accelerate the commercialization of research outcomes, and foster international cooperation and industry engagement. Here are the partners of the HCCC. The HETIA is the coordinator. We'll say a few words about this in a moment. The HETIA is an association of companies. It was founded in 2005. At that time, it was called SIA, Hellenic SIA. And after 2018, it transformed to HETIA to also include things apart from chips. Here are some of the members of HETIA. It's a huge ecosystem. A few words about the institute I come from, the University of West Attica. It's one of the greatest universities in Greece. It has over 50,000 students. It has 6-7 schools, 27 departments, 3 campuses, and more than 600 faculty members. The Faculty of Engineering consists of 7 departments, and one of these is the department I come from, the Informatics and Computer Engineering department. Other departments of the School of Engineering are the Electrical and Electronics Engineering, Industrial Design, Surveying and Geoinformatics, Mechanical Engineering, Naval Architecture, and Civil Engineering. About the Department of Computer Informatics and Engineering, it is the only ICE department in Athens. We every year receive more than 250 students. We have 29 faculty members. We have 12 lab assistants, over 80 associates, and we participate in a number of European funded projects. We mainly target 3 fields: software, hardware, and computer networks. The research labs involved from the part of the University of West Attica is the Computing and Embedded Systems IoT Optimization Lab, the Microsensors Research Laboratory, the Electronics and Computer Technology Lab, the Education Technology and Learning Systems Lab, and Microelectronics and VLSI Systems. About the partners of the HCCC, we have a total of 16 participating partners. As we said, the coordinating partner is the HETIA, the Hellenic Emerging Technologies Industry Association. We have 3 research and technology organizations, NCSR, Demokritos, FORTH, and CERT. We have an associate industry public supporter, the Micro-Nano, the Scientific Society, and we have more than 10 universities. Among them are the biggest in the technology field: NKUA, NTUA, UNIVA, AU, AUTH, DUTH, IOI, of course, University of Thessaly, Peloponnes, Patras, Technical University of Crete, and Hellenic Open University. This here is the span of the partners in the Greek territory. You see that we cover actually the whole land. The HCCC it has a connection with Access. It's the alliances of chip competence centers for enhanced semiconductor services. This is a 4-year coordination and support action that it launched in March 2025 under the EU Chips Act also, and it aims to build a strong, interconnected European network of chips competence centers to enable innovation, facilitate access to advanced semiconductor services, and strengthen Europe's position in the global semiconductor value chain. The partnership categories of HCCC, the partners set up a jointly competence center as a non-profit partnership that constitutes a consortium of partners acting separately and independently to serve the common purpose. HETI is the coordinator, as we said before. Partners have voting rights in the assembly and are organized in categories as follows. We have the Semiconductor Ecosystem Association as representatives. We have the Research and Technology Organization partners, the academic institutions, and non-profit associates partners. Associates and industry public supporters are willing to support HCCC and to contribute to its purpose with specific contribution as defined in respective letter of support and letter of intent. And they can act as advisors to the HCCC or as members in advisory groups. And they participate in the HCCC working groups as advisors without voting rights. The governance of the competence center Each partner designates a person as a representative. The partners' resolution takes place in the partners' meetings. We decide on all critical issues about the structure, organization, and terms of partnership, including duration, renewal or termination, exit of the partners, if maybe it happen, new partners approval in partners meetings. The executive board addresses all critical issues about the operation of the HCCC. It consists of 9 members by the partner categories A, B, and C via elections. So A appoints 4 members, partners B, university appoints 2 members, and the association 2 members. And we have one last member, a reputable person from the ecosystem and the semiconductor industry. The executive board holds ordinary and extraordinary meetings and is valid for 2 years and can be renewed. HCCC operations supports day-to-day management activities and administration via the HCCC Administration Office under the Hellenic Ships Competition Manager appointed by the Executive Board. And the right part of the slide, you can see schematically what we just said. Here we can see the Executive Board and Operations team, the 9 members of the Executive Board, and at the right-hand side, we have Konstantina Tsiapali, the Project Coordinator, Evi Tsinda, the Administration, and Sisko Kolokouvarou, the Administration Assistant. Now about the work plan, the activities and duration of the project. The project is organized about raising awareness on the CHIPS for Europe initiatives promoting service and success stories. This is WP3 promotion. WP3 has to do with the connection to design platform and pilot lines and facilitates access to these platforms. WP4 has to do with technical knowledge transfer and supports interested users in developing semiconductor solutions. WP5 has to do with skills and training and has to do with providing access to training and development of skills. WP6 is about promoting the CHIPS fund and facilitating access to vendor capitals. And of course, WP1 is a project management and coordination package to cover all this. The duration is 4 years and it has started in June 2025. The services is a central theme in the competence center. What we do actually is that we provide services to interested stakeholders. We support the electronic systems and components value chain. We offer infrastructures, training, technology transfer services to drive innovation and build Europe's chips capacity and autonomy. You can see here the 3, 4 work packages, 3, 4, 5, and 6, and the main, let's say, services that we want to offer in each work package. In WP3, we see design tools, methodologies, operational protocols to facilitate access and IP access services. In WP4, we have to do with EDA tools and other software, prototyping and co-development services, digital and AI-based solutions, specialized components and system design. In WP5, we have to do with skills and training, semiconductor fabrication, material sequencing design, embedded systems, IoT, advanced technologies, software and business skills training. And finally, in WP6, we discuss with business, investments, innovation ecosystem. We have connection to expertise, business planning and market research. support to find investments, innovation ecosystem, and networking. In the next slide, we can see some example services and where we target them. So, for example, for silicon IP providers, we provide know-how transfer on operational protocols of pilot lines through participation in the Apex pilot line. For silicon startups, we provide industry engagement, innovation and promotion, design tools, facilitate access and support to find investments, and so on. The results, the intended results of the project, the KPIs, can be seen very shortly in this slide. We target access design platform pilot lines. We target direct benefits of design platform pilot lines, organization utilizing our services, training activities, knowledge transfer activities, and in each cycle you can see the targeted number of services and beneficiaries that we want to target. Excuse me. We target more than 100 events and workshops, and of course, activities in accordance to the access network. There are two sites that we utilize at the present. The main site, the hcc.org.gr, and the services site that it's currently under development, and where very soon, in the next couple of weeks, we are going to present and provide from there the services of the competence center. We have participated in a number of events since June that the project started. In October, we established the Emerging Tech Conference in the University of West Attica. On December, we have the Emerging Tech Forum. It will take place in Athens. And also in November, we will have the Micro and Nano and Chips Tech in Chania. So we will welcome you to these events. I mean the December and November events. And that's all from my side. Thank you very much for your attention.
Thank you very much, Professor, for your presentation. Are there any questions from the audience? No? Okay, Nikos. Nikos had one question.
Thanks, Professor, for the presentation. I have a question actually for the other participants. Can somebody from outside Greece participate or be advanced from this initiative, this Hellenic Chips Competence Center?
So, Nikos, there's a question for me or for the participants?
For you.
You mean to get services, that's right?
Yes,
that's the question?
Yes, that's right.
Unfortunately, due to the fact that half of the project is funded by the Greek government, there is a, let's say, rule that in order to participate, a company must have a VAT in Greece. So, no.
Okay. And as for potential collaborations with others, for example, let's say that a service of Greece, the next step of designing a chip is to test it in radiation environment. For example, this is just an example. Can the HCCC collaborate with, for example, RADNEXT project to continue, let's say, these experiments? Is this feasible to establish this kind of collaborations with other projects?
Of course, we always search for the collaborations. The question is that the idea of HCCC is that companies come to HCCC and get services. So if the question is if we can add, let's say we can act as mediators between a
That's
company.
right.
Yes, of course. The idea is yes.
Okay. Thank you.
Thank you so much for the question.
Right. So thanks again, Professor Villagis, for your presentation. And now I think we have finished with the presentations. So we'll move on to the roundtable discussion. I will hand over the coordination to my colleague Nikos Ketopoulos, who will guide the discussion with our speakers.
Thanks, Akis.
Nikos.
Hello, everyone. So I'm Nikolaos Ketopoulos, adjunct professor at the University of Thessaly, and I'm glad to host this discussion for the next 30 or almost 30 minutes. So let's start from Professor Nikolits. And I want to ask you, how easy is it for a non-EU country like Serbia to find funding? Is national funding sufficient to support research activities? Professor Nikolits, can you hear us? Okay, I will make the same question to Professor Marjanovic, because you are also from Serbia. So how easy is for you as a non-EU country to find funding? Can you hear me? Can anybody hear from?
I can hear you, Nikos. For me,
Okay.
it's fine.
Yes, we hear you, Nikos.
Okay, I will skip the question. And Mr. Soderstrom, can you hear me?
Yes.
Okay. I have a question for you.
Excuse me. Hello. My name is Jelena Nikolic, and I can answer your question.
Okay. So let's go back to the first question.
Okay. From the start of the IDA for Edge project, I have been running this project, and I can say something about IDA for Edge project. As you know, our partners are from the IHP, University of Manchester, and University of Ferrara. And actually, we had a collaboration with partners from IHP, Germany. And previously, before we started trying to apply for the project and in order to obtain funding from EU, and we have decided to try. We have tried once, and then we have tried another one, and the second application was successful for us, and this project is now we have actually 1 year behind us, and everything is fulfilled for now. And it's not easy to apply for funding, and it's not easy to achieve to have projects approved for funding, but with the selection of good partners, such as our partners from IHP and University of Ferrara and University of Manchester. We were actually happy to have some research pipeline well established and recognized by the reviewers and accepted for funding. It's not easy for us, but with good collaboration, everything is possible.
Okay, that's great. Okay, thank you.
You're welcome.
Mr. Soderstrom, CERN is a major player, of course, in Europe, running several research programs for many years and have a broad perspective of all, let's say, innovations in Europe. Do you believe that the quality of research in European Union universities and companies is comparable to that of USA or China?
Yeah, it's of course difficult to answer. In general, I would say yes. I mean, then there are of course specialized fields. I mean, if you talk about research as a general, then it's of course varies a lot between different fields. Then of course, I mean, Europe is trying to be pushing forward with this CHIPS Acts and this development of semiconductors and manufacturing as well, where we obviously are a bit behind still the East Asian production, at least. But yeah, no, I think it's, I mean, we definitely have the, for research in general, I would say that definitely Europe is a strong comparable player to the US and to China in terms of particle physics, especially where CERN is the most focused. Then, of course, I think yeah, CERN is in what they are doing, leading the field in that regard.
That's good to hear from you. Okay, and as you mentioned about CHIPS Act, I will ask Professor Voyadzis about HCCC. This is a new initiative in Greece, and I would say it is the largest project in the field of electronics ever launched in Greece, I think, with 16 participants. So do you believe it will elevate the Greek semiconductor ecosystem, both academically and industrially?
That's a very, very, very interesting question. Thank you very much, Nikos. It's a huge project, huge. It's about 7 million, as you said, 16 participants, partners. It's a special project. What do I mean with this? It's similar to the, if you know, you're familiar with European Digital Innovation Hubs. The idea of the Competence Center and as well as the hubs is that they, as I said, offer services. So what we want, we don't have, let's say, deliverables in the classical, typical way. We have to find stakeholders and to provide services to them. These services are very, let's say, diverse. Most of them, the most, let's say, needed at this moment is educational. So the idea is that we will elevate the knowledge of the people with respect to what the Competence Center gives. But it's not easy because, as I said, half of the project is funded by the Greek government, which means that it will go with the rules of ESPA. ESPA gives, and there's another variable in the equation, which is how difficult it is to handle the project. So, to make long story short, I believe this is a very nice challenge, opportunity. It is not easy to handle the whole, let's say, project, but from what we have discussed with the participants, the partners and the coordinator, we have all the willingness to do the best we can. So, to answer the question in one word, yes, I believe that it will help very much the chip community in Greece. But of course, we will have to go through a series of difficulties to be able to do that. It's not easy.
Yeah. Okay. Thank you. Thank you so much.
Thank you so much.
And as we discuss about competence centers, Professor Floros, I know that you are a newly appointed professor in Dublin. Are you familiar with the Ireland's CHIP Competence Center, and what is its main focus, if you know about that?
Yeah, and the fun fact, the coordinator is a Greek guy also in the it's Yorgos Fagas, so but he's I think 20 years there in Ireland, so he's more an Irish person now. I think the idea is mostly the same. In Ireland, generally, there's a policy that is called Silicon Island, because they're trying a lot to promote semiconductor companies and the semiconductor ecosystem there. I think the most easy part is, let's say, the internal policies of the government for the Ireland Chips Competence Center. It's mostly focused, I would say, on devices and materials. This is the main orientation, but it has access to a broader ecosystem because it has Infineon, Intel, Synopsys, and Cadence, which also big players there, and they're established companies that they're in Ireland. I think these are the main difference. So I think the material approach that they use there.
I see. Okay. And do you see any potential framework for collaboration between Trinity College and other universities in Europe? Is there a set process for that?
A process, it's always through Horizon Europe or any funding opportunities. But I think I would say that the bad thing about the people that they are outside of Greek universities, or let's say in more advanced countries, they have more easy access to regional funding, which the proposals are smaller, and they're not very keen to work on large grants most of the time, or to write the proposal, which is sometimes a very hard and time-consuming part. But for example,
it's a full-time job, if you may.
Exactly,
if I may.
exactly. But for us, let's say, for me, I'm always happy to participate, and I'm also drafting several proposals by myself. So, for example, I'm trying to submit a Marie Curie this month, at the end of this month, and several other initiatives.
Okay.
The idea is
thank
just
you.
to train people to write proposals, maybe, or how you can do it in an effective way.
Okay, thank you. And as we discuss about new proposal, I would like to ask Professor Marjanovic about the next step for RESIST. Do you plan to submit a new proposal in the same field or something like that? Probably professor is not here. So, okay, let's continue about RADNEXT and Mr. Soderstrom. How can academia and industry align their research priorities to accelerate technology transfer, actually?
Yeah, no, that's a good question. They are probably quite aligned already. I mean, both the academia, I think, I mean, they are trying to make up new ways of getting more like resistant devices to radiation and different methodologies and different what have you. But I mean, it's quite the same as the industry, I think, as well, or if they are focused on like providing chips that are, or devices that are supposed to be rad hard then in that case. I don't know, was there some specific something specific you were thinking about there in your question?
No, I'm asking in general, actually, because there are two, in my mind, there are two options. Either the industry will push academia, for example, toward solving specific problems, or academia acts more freely, let's say, to pure distribute innovations. So,
okay, that they
what
are
is your
like
opinion
disconnected
actually on that?
Yeah, no, it's for sure it might be a bit disconnected, and I mean, if the output of one does not feed into the other, or not or it's not possible to feed into the other aspect. But yeah, no, I'm not sure actually if there is what specifically could be done to align this these fields. Yeah, at least immediately I don't have a good answer for you.
Okay, I think, of course, all these projects that brings together companies and universities and research centers, for example, are
no, I
a
mean, for
good
instance, I guess
initiative.
yeah, exactly. The discussion is, of course, the key point here, that you are talking between academic institutions and companies, and if you have a collaboration and a consortium, right, like RADNEXT, then you have like a foundation and a kind of a playing field where these intersect, and you have good communication between the participants, which are both from industry and from academia. And the workshops, for instance, that I mentioned that we have had within RADNEXT, have had representatives from both universities and from many different companies, where ideas can be exchanged, and I mean these conversations can be had, which are necessary to understand from one part to the other, like what is needed, and what the goals are, I guess, from the different participants. Yeah. So yeah, I mean that would be the main part, to have this surfaces where you have meetings and good conversations between the various stakeholders, I would say.
Okay, yeah. Professor Nikolits, from your experience, most projects build on personal relationships between the partners, or by searching the partners. Which is your way to find partners for a project?
I have already mentioned that we have a good collaboration with our partners from IHP, and actually they had a good collaboration with partners from University of Ferrara, precisely with Professor Davide Bertozzi. So we were happy to meet Professor Davide Bertozzi, and he moved from University Ferrara to University of Manchester, and that's the way how we actually connected with the University of Manchester. But everything relies on good connections and with proper approach in doing research and in collaboration. And for now, everything is good. Our project is on good track. So I think it's very important to have reliable partners, and in order to finish everything on time and to fulfill all that was specified in the description of action, actually.
So networking before starting projects is very important, I think.
Actually, I got one advice from my colleague from University of Novi Sad, who successfully finished TWIN project, and he told me that it is very important to have reliable partners because that's the key for success and one of the keys, of course. And we are happy to have this consortium, as I mentioned, that we have.
Yeah. Okay. Thank you, Professor Voyaziz. Oh, yeah. Sorry. Okay. So, Professor Voyaziz, many research efforts tend to end once the final report is submitted, let's say, to the project officers. Why do you think this happens, and what could the European Union do to encourage the continuation of project results?
Thank you very much for the question. It's, how do we say, the elephant in the room? How do we say that? Yes. The truth is a huge number of projects, as you said, finish the day the final deliverable is delivered. Now, the main question is why? The answer is because there is another project that has to start or be submitted for evaluation. So time is never with the projects that tend to complete. It's a matter of how we perceive things. There are a lot of, a huge number of research scholars that have a nice idea and submit the idea, find a good consortium, materialize the project, and then they have, in the meantime, they have found another nice idea, another, let's say, field. What is missing is a long-term design. I mean, you said that some projects were going to have a second, let's say, life and a second submission for proposal. What can the European Union do? I'm not sure. I don't have an answer on this. I have an answer on what we can do as proposers and as project coordinators or participants. We have to have a long-term plan of what we want to do and follow the plan. I'm not sure if I answered the question, or if it's a satisfying question, but for sure it's not an easy one.
Okay. Yeah, thank you. So I will continue that question and I will make it to all of you. Year by year, the expected TRL technology readiness level for EU projects seems to increase. Proposals that include prototypes are often considered more attractive, let's say, than those focusing on pure research. If I'm not mistaken, for the European Union strategy is that the fundamental research should primarily be supported by national funds, like Professor Floros mentioned previously, while product-oriented research is mainly funded through EU projects. So I'm asking to all of you, do you believe this is a sustainable approach for EU funding projects? Whoever wants to answer, please go on.
Just to be sure, the question is if it is sustainable to require more higher and higher TRL levels.
Yes, yes. Because as we said previously, to submit a proposal is a very time-consuming process. The acceptance rate decreases year by year because more and more proposals are submitted.
And ChatGPT generated proposals.
Yeah, sure. And I think that in order to make more attractive the project, you have to, let's say, provide a full solution. So naive research or pure research seems to not be so attractive to Europe to make a project, to accept a project. So I'm asking about how hard is to submit a pure research with low readiness level, and how can we continue doing pure research in this context without funding, of course?
Of course, it's not easy to do research without funding because, you know, candidates, PhD candidates that actually do a part of the work always need some funding to get to live on it. The idea is that basic research is a fundamental field in research. So we always need to do research if we want to have applied research and making products, of course, is a good thing. But if we don't go back to basic research to discover again things, new things, we can do actually innovation. I don't know if this sounds very, let's say, revolutionary, but if we keep on doing just application things, we can't go much further.
Okay, thank you. Thank you.
Personal opinion.
Is anybody that wants to add something on this question?
Yes, Nikos, just also from my side, I think there are also some opportunities, like it's the Pathfinder challenges that they're very low level TRL also, where you can find some more primitive research concept. And you can also change between research and innovation action. So you see that research and innovation usually has lower TRL and innovation action goes up to more higher. Also just a note from my side.
Yeah, sure. Okay, And one more question to Mr. Soderstrom. From your experience, what is the most challenging aspect of coordinating an EU project with multiple partners from different countries and different institutes?
Yeah, luckily I am not personally the coordinator of the project, so I don't have to be the person in charge of it. But of course I help with this in some regards. Mainly what I am looking after in the project is mainly this transnational access part of it that we have. And of course, the main challenge is when there are so many people and many institutions involved is that it's always like a slow process with a lot of inertia to get all of the participants going in the same direction. And it requires a lot of repeated communication, of course, and being active. I mean, it takes a lot of time and a lot of effort to get some things done. Which is, I mean, of course, you have to take that into account when you have a large project that you have to spend actually some effort to do all of the tasks, even if they seem easy on paper. But it requires a lot of follow-up and continuous communication in that sense.
I see.
Yeah. So I guess that's the main part. But then, of course, it's rewarding as well when you have large amounts of people doing the same thing and going in the same direction. Then you get good results in the end if you manage to get the ball rolling, so to speak. Then you can have good outcomes as well.
So I think coordination is more hard than the technical problems and challenges.
No, exactly.
Okay.
Yeah.
Thank you. I think that we cover several important topics in this short session. I want to thank all of you for your valuable contribution. I hope that you found the discussion interesting, and perhaps it can serve as a starting point, let's say, for future collaborations. So thank you all once again.
Thank you very much, Nikos. Thank you, everyone.
Thank you, Nikos.
Thank you.
So,
Congratulations.
closing this first webinar, I would like also, on behalf of the TWIN-RELECT project, to thank all the speakers for accepting, of course, the invitation and for their contribution. And also all the participants, of course, for being with us. Hope you gained valuable insights into the recent developments and collaborations in electronics design and semiconductors within the Europe. Thanks again, and we look forward to seeing you in the next events that will be organized either from TWIN-RELECT or from your projects as well. So thank you from my side.
Thank you so much.
Akis, I have a question. Are the material of the webinar will be available to all the participants?
The material of
the presentations or the recording?
the recording, yes, will be
Okay.
uploaded on our site.
Okay, thank you.
Perfect. Thank you so much.
So have a nice rest of the day, and thank you very
Weekend.
much again.
Have a nice
Nice to
weekend.
see you all. Bye-bye.
Bye-bye. Thank
Bye,
you.
guys.
Bye.
Bye. Thank you.